Hello everyone. This presentation will be about LIN Fundamentals. Its purpose is to give an introduction to the LIN protocol and hopefully answer a few questions that you might have on it. In this presentation, we will first describe what LIN is, look at the physical layer. Next, describe the data layer, look at the application layer, and then conclude with a few points to remember. Let's get started. LIN, what is it? LIN stands for Local Interconnect Network. LIN was created in the 1990s by a consortium of 5 auto manufacturers. The idea was to create something a little more cost efficient for controlling systems that didn't need too much data too quickly. If you didn't need to spend the money on something high speed, where possibly that was built in the protocol to begin with, LIN would be a good choice for you. As cars have become more and more complex, you'll see more and more computer systems in them. A lot of these systems are running on LIN. LIN provides a cost-efficient communication where bandwidth and versatility are not required. Again, if you don't need to spend the money on a system to send data quickly or in large chunks, LIN would be a good choice for that. It's less expensive. The components are less expensive. It's less expensive to set up. That was the idea behind it. If you could save money that way, it could help lower the overall cost of the vehicle. The physical layer will show that a little better. Think smaller, slower, a little less power. The physical layer, the wire itself, it's a single wire with ground and power. So sometimes you might hear it's a single wire channel, even though there's actually 3 wires inside the wire. But that's the basis for it. Nodes operate between 8 and 18 volts. You won't see high voltage on a LIN. Lower power means less to run the system, basically. So smaller nodes, a little less power to operate them. It works on the slave principle, single master, multiple slaves, up to 15 slaves. Different protocols can have more nodes on them. If you don't need that many nodes, why pay for a protocol that allows you to have 100 nodes on it when you're not going to need them? Something I wanted to point out too is that the master on the LIN bus can also act as a slave. Many protocols require you to have 2 nodes on them so that the 2 nodes can communicate with each other. With LIN, because the master can act as a slave, it basically can talk to itself. Speeds, like I mentioned before, are slower, 1 kilobit per second to 20 kilobits per second, roughly. Other protocols can go faster, but if you don't have that need to communicate faster than that, again, why spend the resources to do it or to have that in place if you're never going to use it? Your overall size of the bus is about 40 meters max. I have never seen a car 40 meters long, so overall that 40 meters should work. The way you see a lot of LIN systems work as well is that they're part of a larger system. So that master and slaves, roughly 10 to 15 nodes, might connect into a larger bus. So you'll see what's known as a LIN cluster plug into a larger CAN bus. And then it communicates that up to a larger trunk. So let's say you have a smaller system that works the turn signal. Just something simple like a turn signal. One node will say if it's turning right, one node will say if it's turning left. It'll communicate what's going on that LIN cluster up to the CAN bus so that a larger computer system can tell what's going on, possibly do something from there. That's just some of the possibilities that you have with LIN. Now, looking next into the data layer, this is where you start to see a little bit more. LIN uses the master-slave principle as mentioned with the nodes. What that means is that a single master controls several slave nodes. It sets the tone. It sets the tone for the entire bus. All messages are initiated by that master. The master sends data out or asks a node what's going on, and the node replies. The node itself won't put a frame itself out on the bus on its own. The master also controls how messages are sent. That will allow for better control to avoid collision. The master will set the timing. It will tell the nodes the speed of the bus so that the slave nodes themselves will auto-baud to what the master wants. Here is how the LIN system communication works. The master itself actually creates the frame and puts it on the bus. What it does is it fills in the header. The header has various information on it that helps describe where the frame is going. The slave node checks the ID in the header to see if it's for them. If that frame is for them, then the slave fills in the data and places that frame back on the bus. So the slave doesn't actually create the frame, it just fills it in. You can look at it like this. A form on a website, you go to fill it in, but it already has your name filled out, your phone number, and your email. You could think of that as the header. You fill out the rest of the information. Maybe it's a website where you're just trying to send feedback, a paragraph of feedback, and you're the one filling that in. It already knows your name and your phone number and your email. It's already got that filled out, so you just have to fill in that data part. It's along the same concept. Looking at the frame is split into two parts. There's the master header and the slave response. The master node is responsible for creating the header, and then the slave node is responsible for filling in the data. The header is broken into three parts: the break field, the sync field, and the protected identifier field. The response can be a variable length. So when the slave adds the data to the frame, it can be in a variable length. In version 1.0 of the LIN specification, the lengths were set based on the frame identifier value. In later versions, only the diagnostic frames have a set number of data bytes. We'll discuss what diagnostic frames are later in the presentation. All other frames carry between 1 and 8 bytes of data. The number or the amount of data contained in a frame with specific frame identifier shall be agreed upon by the publisher and all subscribers. In other words, it's determined by the system designer. Let's take a closer look at the master header. Like I mentioned, the master header is comprised of three parts: the sync break field, the sync field, and then the protected identifier. The sync break field is roughly 13 bits long, and it is a dominant bus low condition. This is to ensure that the bus will see it as a break. This is the space between frames so that it knows that a new frame has been placed on the bus. The sync field is what helps the slave node determine the transmission rate which the master node is using. This is what allows the auto-baud detection by the slave nodes on the bus. The protected identifier field is actually made up of two subfields. The first 6 bits is the frame identifier. This is what tells the slave node that this frame is for them. This frame is what you are going to need to use. The last 2 bits are used for parity. The protected identifier field, that 6-bit identifier in the first part of the identifier, that contains info about the sender and receiver. If the range for that is between 0 and 59 decimal, that is a normal signal data carrying frame. If it is between 60 and 61 decimal, that's for diagnostic and configuration frames. If the ID is 62 or 63 decimal, that is reserved for future use. We'll talk a little bit more about the normal signal and the diagnostic configuration frames in a little bit. Let's take a look at the data field now. Now, based on that identifier, like I just mentioned, that's how the slave knows what's going to happen. That's how the slave knows it's for them. If that slave node has data, it starts putting it into the response field. The data bytes are transmitted in least significant byte first format. At this point, I wanted to make a quick mention of checksum calculation for LIN. Checksum calculation over the data bytes only is called classic checksum, and it is used for communication with LIN 1.x slaves. Checksum calculation over the data bytes and the protected identifier is called enhanced checksum, and is used for communication with LIN 2.x slaves. I wanted to point out that difference because there is one. Now let's talk about the types of LIN frames. There are 4 that we're going to be discussing today. The unconditional frame, the event-triggered frame, sporadic frames, and diagnostic frames. The unconditional frame is your basic frame. This is the frame used most often, and it's just the common frame. The master creates the header, puts it out on the bus, says, okay, node 1, I need some information from you. Node 1 places its data on the back in the frame and puts the frame back on the bus so it can be read. Common, simple. An event-triggered frame works a little differently. With an event-triggered frame, the master has sent out a notice that when an event happens, the nodes respond with data. So instead of one at a time, master sending out header, receive data, header, receive data for the frame, sending out frame at a time, it pre-writes a lot of, you could say it pre-writes that frame, puts it out on the bus, like, okay, when X happens, fill it in and let me know. So when X happens, node 1 knows that the event happened and fills in the rest of the frame. There is a very good possibility of collisions happening in this process. Think of it like when a teacher asks a question to their class and everybody in the class just starts yelling out answers. What does the teacher do in that situation? That's when they say, okay, everybody raise your hand and I'll call on you one at a time. That's what the master does. When it notices collisions occurring, it switches back to the unconditional frame. And it goes back to each node and goes one at a time for data. With the event-triggered frame process, you can get a better bandwidth, slightly better bandwidth. Reason being is because a lot of the pre-work's already been done. Instead of trying to hunt each node down, so to speak, on if it has data, the nodes just give it to them. Just gives the master data from there. So you can get a little better bandwidth. You just have to be prepared for collisions and then switch back to the unconditional frame system or the unconditional frame process. With sporadic frames, you have a hybrid of the two. In this situation, the master might have some process that knows when a node might have data. If it thinks that the node has data, it will go out and say, okay, node 1, in this I believe at this point you should have some data. If it does, then the node 1 responds back. Now to compare that to the unconditional frame where the master might say, node 1, send data. Node 2, send data. And maybe node 1 has data, node 2 doesn't. So it just sends back a no response for node 2. The master has an idea that one of those nodes has data. So instead of searching through each one, it's a little bit more choosy on which node to ask for data. The last frame type that we're going to discuss are diagnostic frames. These frames are what set up event-triggered frames or sporadic frames. They're a little different than other frames we've discussed. They're different in the respect that they are always going to be 8 bytes long. Whereas you might have set up a different length before, a diagnostic frame is always going to be 8 bytes no matter what. They also have specific identifiers, 60 decimal or 3C hex and 61 decimal 3D hex. The way the diagnostic frame works is that the master starts sending out, okay, we need to do something a little different. It tells the slaves, this is how we're going to operate on the bus for a while, at least until it decides to change it again. And what happens is that if you send out that 60 decimal ID, that'll specify what information is needed from the slave node. So the master writes all 8 data bytes, telling the slave what to do. If 61 in decimal is placed out on the bus, so the slave can respond to the request. The slave provides the data bytes. So the slave basically responds back using that 61 decimal ID. You may need to send the 61 decimal ID multiple times to get the full response from the slave. Now, how does a master know it's a master and a slave knows it's a slave? And how do they know what speed they're going to go at? And how does the system know what it is? How do you describe what the LIN system is? That's where we look at the application layer. So on the LIN bus, how does it know what node is a master and what node is a slave? It uses the LIN description file. What the LDF is, it is a simple text file that is used to discuss how we describe the system so we know what nodes are on the cluster, the rate of communication, etc. This is normally processed by a tool to generate the configuration for a LIN device driver. This file is what tells the node or the nodes what it's going to be doing. Here's an example of it. As you can see, everything is formatted. There's different sections of the LDF. The top part, the LIN, designates a LIN description file. That's how the system might know that this is for a LIN description file. This will tell the LIN system, hey, this is what you are. It also mentions the LIN protocol version and the LIN language version. Do you remember a few slides back I had mentioned the checksum? This is what sets that checksum. Like this is what it says. This is what a lot of that's based off of. Where it says the 1.3 there, that means that they're going to be using the 1.x checksum style as opposed to anything 2.x. That, again, that right there sets the tone for it. It's setting the speed of what the bus is going to be set at. This will tell the master and the slaves what the frame and the header is going to be at. It has description of nodes, signal types. I want some of these slave nodes are, and everything is in a specific format. Everything is laid out just like this. You want to go in this order and make sure you have this information in there. It doesn't look, to me, it doesn't look any different, or it's all in the same concept as like a JSON file or possibly XML, where you need that format to it. And by reading through it like this, it's fairly descriptive just on its own if you want to look at it. It's not too intimidating, and this is what can help set up your LIN bus to make sure you get things the way that you want it. So now that we've talked about the physical layer, the data layer, and the application layer, I just want to give a quick summary on everything that we've just talked about. LIN, it's less expensive but less robust. If you don't need the bells and whistles, why pay for it? LIN works. It may not be the fastest. It may not be able to send the largest chunks of data, but it does its job. And it does it pretty well. LIN works on the master-slave principle. One master controlling multiple slaves. One master setting the tone for multiple nodes. The LDF describes the LIN bus. That is the configuration file that you need for your LIN system. If you do have any questions, you can always contact us at support@kvaser.com. And I hope you enjoyed this presentation. Thank you.
Thank you, Adam, for that overview of LIN protocol and message structure. We're now going to speak a little bit about CANLab software, its LIN hardware options, do a little comparison between LIN and CAN. We're going to configure CANLab for LIN, talk about the data file, schedule table, and then do a live demo. So CANLab is a multifunction bus analysis tool, allowing for the recording of signals, sending and replaying of messages, while also incorporating a scripting environment. CANLab is a complete network analysis tool for CAN, CAN-FD, and the focus of today's presentation, LIN. And because CANLab is a Windows-based tool, it has common Windows toolbars and menu bars that help new users quickly acclimate to the software. CANLab supports LIN, or the Local Interconnect Network. Since LIN doesn't have the speed or arbitration of CAN, it is used in secondary non-critical applications such as windows, sunroofs, seat position, or occupant detection. ATI's CANLab currently supports ATI Canary CAN with LIN interface, as well as Canary FD, multiple Kvaser CAN interfaces, and will shortly support the Kvaser LIN Hybrid hardware series. When we first open up CANLab, we're presented with a blank window. And over to the left-hand side of that window is the navigation panel. This navigation panel is where we can set our hardware up in the channel manager. So again, we support several ATI and Kvaser CAN, CAN-FD, and LIN devices. It's the channel setup that is the only portion of CANLab that must be done while offline. After the hardware is configured, including setting its baud rate, everything else can be done online and live while collecting data. A few of the hardware options that are available to us is the Kvaser Leaf Pro LIN. This is a single channel LIN device, LIN dedicated device. And that is what I'm going to be using for my demonstration today. Kvaser has also launched a hybrid device, which can be purchased in either a single or dual channel device. And that allows you to dedicate that CAN channel to either LIN or CAN as required. So in the context of the Kvaser Hybrid CAN-LIN interface, it's a one-channel device which will allow you to either bring in LIN or CAN traffic. In the case of the 2-channel device, which you see here, this will allow you to bring LIN on either channel or CAN on either channel, or bring in LIN on one channel and CAN on the other. ATI's Canary hardware also provides for 2 CAN channels and or 2 LIN channels as required by the user. Now, one of the first differences between CAN and LIN is the pinout for the hardware interface. So here you see a typical DB9, which is used on all of the Kvaser and ATI CAN interfaces. And here we see your typical CAN pinout, where 2 is CAN low, 7 is CAN high, 3 is ground, and 5 is shield. When we look at a LIN device, we see that 3 is again ground, 5 is again shield, but now 7 is the LIN bus and 9 is the reference voltage. Looking at the ATI Canary with LIN, we see a similar configuration where reference voltage is 9 and the LIN bus is dedicated to its own pin. Here we see an example of the difference between CAN and LIN. Whereas CAN has multiple nodes, LIN has a single master and multiple slave modes. LIN is a much slower bus rate. CAN uses a twisted pair with a 5-volt offset for its messaging. LIN uses a single wire at a 80% offset. CAN can have either 11 or 29-bit identifiers, whereas LIN uses 6-bit identifiers. Here we see an example of how the LIN and CAN messages look on an oscilloscope, where CAN is a 2-volt differential signal between CAN high and CAN low. LIN is a single wire that is driven either to 0 and bus voltage, where below 20% of the reference voltage is dominant and above 80% is recessive in its bit configuration. As Adam mentioned earlier, there is a significant difference in the way CAN and LIN have their messages configured. Here again we see a much smaller data field, a very small arbitration field, and of course there is no arbitration in a LIN message. Typical LIN applications are again typical slower, less critical functions in the vehicle, such as light controls, light sensors, sunroofs, cruise control, seat positions, grille shutters, small motors and mirrors such as window control and mirror control. Cooling fans, this is where LIN is becoming more and more prevalent in the EV market as they use LIN to drive the coolant system of the electric vehicles. So here we see an example of the CAN and LIN bus integrated into a single vehicle platform. Whereas we have the high-speed CAN bus operating engine, ABS, powertrain control systems, and then the low-speed handling more comfort amenities such as seats and air conditioning and door motors. LIN is actually driven off a master which receives information from the low-speed or high-speed bus through a gateway, then converts those messages down into a LIN message for broadcast on the LIN bus and action and response by the various sensors and actuators. Here again is another closer representation of the master, which in this case would be a LIN stalk for turning on and off the windshield wipers and turn signals, where the master broadcasts out on a single bus to each individual sensor and motor and waits for a response. The LIN Database file, or LDF, is similar to a DBC file in that it describes the behavior of the local network. The LDF is used to configure and create the scheduling behavior of the LIN cluster, as well as defining the messages. Schedule tables make it possible to assure that the bus will not be overloaded. They're also the key component to guaranteeing the periodicity of the signal. Within the CAN trace object of CANLab, we have the ability to display the messages and signals within. The CAN trace object has two LIN-specific column options, framing and timing data. These can be accessed while in the CAN trace object by right mouse clicking the headers and select Runtime Column Customization. So now we're going to see a live demo of CANLab. So here, as I've said before, this is the blank workspace within CANLab. Looks and feels much like Windows. Much of what we're going to do is going to be mouse driven. And you can see at the top you have your menu and toolbars, and then to the left we have the navigation panel. So the first thing we're going to do is we're going to add a CAN channel. In this case, the Kvaser LIN. So I add the channel. I assign the device, because I could have more than one CAN or LIN device in my workspace at any one time. And because CANLab is going to be acting as the master in this demonstration, I set CANLab mode to master. If I was just going to be watching the bus, I would leave it in the slave configuration. I add my LDF file to my database manager. And again, I can set this to all devices or a specific LIN or CAN device as necessary. Then I configure my LIN monitor. This is where I'm going to set my schedule table. And of course, I could set multiple tables or multiple schedules within, depending on my hardware configuration. I add a CAN trace object. I go online and I start to broadcast my LIN data. So I'm going to right mouse click and hit Fix Message Position. And then I'm going to expose the signals inside of the message. So we're going to open up the columns here a little bit so we get a better view of what's going on inside of the message. See my flags, my message ID. See whether or not I'm transmitting or receiving. If I was transmitting, this would be R with a green arrow. But because I'm transmitting from CANLab to the device, I'm showing a T with a black arrow. Shrink these down a little bit, get a little more real estate on my screen. I right mouse click in the header section. I hit Runtime Column Customization. I scroll down and I grab my LIN frame data and my LIN timing data. And I can now see my frame and timing data as displayed on from the bus. Now as I toggle the switches, you'll be able to see the messages change, such as the front washer, the front wipers, my right turn signal, my left turn signal, and so forth. I can also show this information graphically by adding a scope object. Drag my scope down here so I can see my trace and my scope at the same time. And I'm going to grab my turn signal switch, drag it down to my scope. And now, as I toggle between right turn switch off and then left turn switch and off, I can see these signals displayed graphically in my scope down here at the bottom. That concludes the live presentation or the live demonstration of LIN. If you have any questions about purchasing or questions about the hardware or software, you can reach out to us in your local market. We have offices in the US, India, Japan, China, France, Sweden, Germany, and the UK. So you can speak to a local representative. Of course, you can always check out Kvaser.com or AccurateTechnologies.com for more information on the web.